Okay, so, oh no, not this one. Got to the wrong screen share. Should be, where is my, hold on, okay, let me find, where is that? Okay, it's here. Okay. So what today we will start. If you recall, last class, we discussed the concept about multiple layer perceptron. So MLP, we may see this a lot, okay? And basically it's artificial neural network. So neural network in machine learning, we always hear this, etc. So the concept behind it. And so the very basic idea, let's just remember it's using feed forward. Feed forward to do the prediction and to do the training, but at the same time, it also uses back propagation. For the calculation of gradient descent. Okay, so that's a major difference between multi-layer perceptron and the previous that we learned, just a single layer ones. Okay, at that time we just have feed forward, we don't have back propagation. Okay, and here it's use of back propagation. So using the arrow. So arrow is a back prop from output and then to hidden layer. Okay, and then to the next hidden layer. Using this arrow and then find the relationship between the arrow and the gradient descent, because the gradient descent then will help us to adjust weights. So the neural network, the overall concept is we keep adjusting weights until we find the optimal one. Okay, then we can do classification. So we understand the concept. So today let's take a look at the example. Okay, so the first example is also from the classic machine learning data set repository. Okay, and it's about the wine data, about wine. Okay, and so we have the data. So it looks like this, and then we are going to do some classification. So it has some number of features. Okay, so that's, so here we have the basic idea about the data. So we use the describe. Okay, and of course here we also transpose. Okay, so total samples we have is 178. Okay. Okay, and so the features we have is about 13 features because we use one as our target. Okay, so this part is the same as usual. We just do train and test splitting, so nothing new. And we also, if you recall, when we discuss a neural network, that and we also prefer to do data scaling. So here we do the standardization scaling of the data, okay? And then we transform our data. So here we transform the data. Okay, so nothing new here. And then, so in order to use the neural network, so from sklearn, we have the package neural network, and we can use the MLP, so multi-layer perceptron. So it's called a multi-layer perceptron classifier. Okay, so we can import this model. Okay, and once we have this model, we can initiate this model. So here you need to provide the hidden layer size. So here we have, so this size means the hidden layer. If you recall, so we have input layer, then we have a hidden layer. So here it has 3 hidden layer, that the neuron size is 13, okay, and 13. And 13, so 13 hidden layer, and then you have the output layer. Okay, so over here to use 3 hidden layers, and this is for the maximum number of iterations, is it? And then we train the data. Okay, so this is also similar as what we have learned so far with all of the sklearn models, is it? So pretty similar. Okay, so you initialize model, then you plug in the training data, okay, to do the training. And here to also give us some explanation about the MLP classifier from sklearn. Okay, and here the activation function is not what we previously discussed. As previously we discussed, we can just use a linear activation function, or we can use sigmoid activation function. This is another kind of activation function. Okay, later on we will explain. And in later on, when we see the TensorFlow, we will also see we use this one quite often for the activation function. Okay, and this alpha basically is for the regularization. Okay, regularization and batch size. Okay, and so hidden layer size and the learning rate. So there are quite a number of parameters, and you can go to the official documentation about the MLP to get more idea. Okay, so here we just gave an example. Okay, about that activation function. The ReLU, okay, so basically it's called a rectified linear unit. Its format is like this. Okay, so X is the input value to a neuron. So it just take between 0 and the input, pick the maximum one. So basically from this, we can know that it always pick either 0 or a positive value. So if you draw that, it's kind of like something like this. Okay, so that's called rectified linear unit, ReLU. Okay, because later we will also see this quite often. Okay, and for the deeper neural network, this can better do the better training, is that compared to some other one. So it says before 2011, we use logistic sigmoid quite often. Sigmoid then, or the hyperbolic tangent. Sigmoid, if you remember, records something like this, is it? So 1 and -1, so squashed. Okay, So that's prior to 2011 that we use sigmoid quite often for activation function. But after that, better trained, then researcher found out if we use this ReLU rectify linear unit, it can provide a better training. Okay, it says the use of as a nonlinearity. Okay, it says has been shown to enable training deep supervised neural network. Okay, is that without require unsupervised pre-training. Okay, and also its advantages allows faster and effective training of deeper neural network architectures. Okay, a large and complex data set. Okay, so it has a lot of advantages compared with others. Okay, so keep this in mind. Okay, ReLU. So that's also the by default one if you don't specify. Okay, unless you specify. And here there are also some concepts because later on when we see TensorFlow, okay, we will also see. Here it also has a concept, it's called sparse activation. Okay, sparse activation is in a random initialized network. It says only about 50% of hidden units are activated. Okay, activated means the input and output that here says non-zero regarding the activated. So another 50 is 0. So not all the weights are going to be activated. Okay, so later on we will also see in TensorFlow, we call it like a dropout. Okay. And overall, previously the discussed concept is also better gradient propagation. Okay, that's fewer vanishing gradient problems if we use ReLU as compared with sigmoid. Okay, so that's why we also so a lot of cases we also prefer to use ReLU. Okay. And it says it's also efficient computation. Okay, only comparison, addition, and multiplication. Okay, not like sigmoid. So that's its advantage part, ReLU. So just keep this in mind. Okay, that ReLU. Okay, it's new to us. Okay, basically it's just take either 0 or positive. From input. So that's, this is serves as activation function, okay. So keep this in mind, okay. And then we can, just as usual, after you do training, you can do testing, predict the value as with testing value, okay. Then we can collect the performance measuring. Okay, like a classification report, a confusion matrix. Okay, so all of those concepts. Okay, so basically for this one, we can say it's quite straightforward. Okay, with that MLP classifier. And next one, let's see, that's about wine data. Next one is about that MNIST. If you recall, that's basically, it's a very basic kind of image recognition. It's just a digit. Is it a single digit? Handwritten, okay. Handwritten digit recognition, is it with a lot of samples. So previously we already saw that. Okay, so we have, so this time what we will see is we are going to use the neural network to do the classification training about handwritten digits. Okay, And over here, we also use sklearn. So from sklearn, it also has this classic data set repository. So we can just go ahead to use it. So we have the data, if you recall previously, the shape, is it? So that's the features. Quite a lot. That's because it's 28 by 28 pixels. Is it? So that's why we count. We have this 784, okay, and we have 70,000 images, okay, handwritten images. Okay, so then the same thing, the first step, what we do is train and testing, data splitting, is it? So we have training data, we have testing data. So this is as usual, pretty simple. And previously, if you recall in our previous chapters discussion about, we can also show the image, is it? Just using a pie plot, okay? So the image show that, but then in this case, you need to reshape what is the specific data because it's 784, is it? But if you want to show, you need to show the 28 by 28 pixels. And then we got the first 5 samples. And here it gave us an idea about what the data is it shows. This is just one specific, a single specific one. Is it? It's 784. Is it? So the number value is between 0 to 255. Is it? Okay, so that's all regarding image. Okay, the pixel value. Okay, and then over here, same thing. We first do data scaling. And over here, we choose the standardization. Okay, and then we train data, etc., and we transform the data. Okay, both for training and testing. Okay, and then what next is similar. We import the MLP classifier. Okay, so we use this classifier, and this time we just a single hidden layer with 50 neurons. Okay, 50 neurons. We also specify the solver, and if you recall in our last class, we also discussed is it a solver. We can choose different. So this is about stochastic gradient descent, SGD. Okay, it's a stochastic gradient descent. Because it's a stochastic, so it supports online. Is it? So online means it supports mini batch. Okay, so that you don't need to load all samples into memory at the same time. Is it? So it's ongoing ones. Okay, and this verbose. So if you set the verbose, it will show you the, for each iteration, it will give you some output. Okay, later on we will see. Otherwise, you won't have the result. Okay, and then we fit the training samples, that fit the training samples, and then for the testing data set, then we can do the prediction, and we also collect the accuracy score, okay, with the testing data. Okay, so that's the general idea, okay, about this MLP. One more example, and here, this verbose, and because we set this verbose data, that's why it has all of the intermediate reporting. Okay, during training. Okay, during training. So for each iteration, you report the loss. Report the loss. This is if you recall, is that the best scenario is with the number of iterations. So here is a cost, or we call it a loss, is it? And here is a number of iterations. So it should go like something like this. Then that means the loss is decreasing with the number of iterations. Is it? So normally that means your result will be good. Is it? So here it collects. Is it? After the fifth iteration says the loss does not improve. Is it? More than whatever we set up the tolerance. So this tolerance is regarding the difference between each iteration, as if for 2 consecutive epochs, so that we stop. We don't need to go to the maximum number of epochs 10, is it? Because you set as 10, is it? But then we also have this offset calculated, is it, between the loss. So if it's even less than this tolerated, then you can stop, is it? Okay, and the accuracy score we can also say is quite good. It's above 90%. Okay. Okay, so that's regarding this example. And then the last one, let's see. So the last one is also, the data is also from the classic machine learning repository from the UCI. Okay, so this is about the diabetes data set. And we also discussed previously, okay. So that's not, so we already know of this information based on our previous discussions. And so it's privileges of the data cleaning work. Okay, so, and then we can start to do, so in this example, we do the model selection, not just a single model. Okay, so, and based on the data cleaning, we also select the features. So in this case, keep all the features. Okay. So in this example, what it's going to show us is we will have multiple models, not just a single one. That we have the KNN nearest neighbor. That we also have support vector machine, logistic regression, decision tree, and the Gaussian naive Bayes, and this one we haven't learned. Okay, a random forest we learn. Okay, gradient boosting we haven't learned, and this MLP. So this is for the neural network. But anyway, so here we are going to see all the models put here, and as usual we do testing data split, cross validation. We learned, okay, the stratified k-fold previously we also learned. So this is to keep, when you do the splitting, you're going to keep the class balanced, okay, the sample balanced between the classes. Okay, and then, so over here, what we will do is we set up a model using a list to store all of the models. Okay, so then we just keep appending, is it? So it's a key value pair kind of, is it? You have the name of the model and the model itself. Okay. And then we do the data splitting, so nothing new here. And then for the next part, is it? So with that model, is it? Then we can get the name and the model. And then we do fit for each of the model. Then we can predict the testing data. Then we collect their accuracy score, is it? Okay, so then we can collect all of the accuracy score, is it? And then from this, we can kind of see, is it linear or logistic regression is good, is it? And random forest is good also, is it? The neural network, you can see it's not good in this case, is it? So it doesn't mean that if you have neural net, it will guarantee it's good, is it? It's just in different scenario, okay? Also based on the data set size and all sorts of factors. And what next is try to do the k-fold cross validation. Is it previously we already learned? Is it, so this is regarding the fold. Okay, then we call the cross validation. Is it score? And then for each of the model, we are going to apply that. And then after we do this, you can see with the neural network improves a little bit, but still not compare with others. The logistic, random forest, still not as good as those. Okay, and so what this is just the plotting about the accuracy comparison. Okay, so not a lot of new things. And what the next one is about the feature selection. That for feature selection, previously we discussed using a different approach. So here in sklearn, there is also feature selection. You can use it called RFECV. Okay, so we can also use this. So let's see, how do we use this? So here it's regarding logistic. So the first one is regarding logistic regression. And for this logistic regression, the solver is to pick this LBFGS, okay? And then what it's going to do with the feature selection is you just plug in. So this is the training model. Okay, this is regarding training model. So you put the training model for the estimator, okay, and then you feed it to the RFECV, okay, for the feature selection. And also you can select the scoring. So this is similar, if you recall previously, we discussed, it's pretty similar with estimator, with scoring and cross validation. And then over here, we plot the score versus the number of features, because this is regarding feature selection, is it? Then you can see kind of, is it? So if you pick 4 features, 5 features, 6, it doesn't make a huge difference. But if you just pick 1 versus 4, there is a huge difference, is it? So basically from here, we can see 4 features will serve enough, is it, in this case? Okay, so that's regarding this. And then you may say, how do we find the features, is it? So then from the result, is it? It will provide us some supporting information about feature importance. Okay, feature importance. Then we can get the top picked. So here they pick the top 5 features. So the 5 most important features. Okay, based on what we just ran the result for feature selection, okay? And then with this, you can just use whatever of a new feature, is it? And then retrain the data, is it? Retrain the data. And then we can also collect the score, is it? Then we can see with just the 5 features, the result is still the top one, is it? 77 among all of the models, is it? So basically that just means this 5 feature will serve enough when we do the model training, okay? Okay, so that's regarding this one, and you can also try with other gradient boosting, that same thing with feature selection, okay? And then it gives us a similar result. So about 4 or 5 features, is it the accuracy won't make a huge difference. Then same thing, we pick the most important features, is it? And we can get the score. You can see it's also pretty close, is it, to you use the full feature set. Okay, and what is the next one? If you recall previously, we also learned the grade search, is it grade search? So with the grade search, we can do parameter tuning, is it parameter tuning? So here you need to provide what parameter you want to tune, is it? Like the regularization value, is it? And what one you're going to use for the regularization, L1 or L2, is it? Or the solver, is it? Sometimes solver also important. What kind of solver you want to use, is it? So here it also shows, is it like for solver, you also may pick the different solver, is it? Okay. Okay, so that's then what we can do is we can do the grade search. Grade search, then you need to plug in which model you want to use, is it? And the scoring. Because sometimes, if you recall previously, we also use ROC, AUC. That, if you recall, you can also use those for the scoring, is it? Then we can do the training, is it? So after we train the model, is it? And it will give you the best parameter and the best estimator, is it? So for regularization value, then 1 is the best, is it? And also it use L2, is it? And solver it to pick the linear one, is it? That's bad. And then for the logistic regression, then here to give you the full one that it used for the training, is it? Use whatever it picked here, okay? So we can say it's C is 1, that penalty is L2, the solver is this, is it? So this is regarding parameter tuning. We can use the grade 1, okay? And after that, then you can just use this as a model, is it? And do the retraining, is it? And then we can collect the result, is it? Then in this case, this is the best result, is it? We can get based on the provided data set, okay? Okay, so that's all of the information regarding the MLP learning, okay? And then let's see, next, what we are going to start. We still have some time, okay, so let's just start with the TensorFlow. You may hear this a lot, the TensorFlow, okay? So this is very helpful for deep learning, okay, deep learning. So TensorFlow is one of the most popular deep learning, because right now we hear deep learning a lot. So basically it's still the concept of neural network, okay? But it's much more complicated. You can build it, okay, with all sorts of features. So later on we will see. And using TensorFlow, the idea is it can do parallel processing. Because basically with machine learning, we can also kind of observe is it can do the parallel process. But so far, with all of our models, even though at some level we also have parallel processing, not none. That if you recall, there is a parameter called jobs. Is it? So that jobs can support multi-core processing. Okay. So, but here it says by default, Python is limited to execute only on one core, as it is that's due to this global interpreter locker issue. Okay. But even this, we still take advantage as it multi-processing library, as it within multi-cores. Okay. But like over here, the desktop hardware rarely it comes with more than 8 or 16 cores, etc. So even though you initiate, you activate, you enable this jobs parameter in all of our previous learning model, like SVC, logistic, those models, etc. Still has very, because in the real world, the data size is huge. Is it even with just that MNIST, we can already see, but MNIST, the image is very low definition. That is just 28 by 28 pixels. But in the real world, think about it. As it won't work. It's much more complicated than this case. Is it? So the solution to how we take advantage of machine learning's benefits using parallel is GPU, okay, graphic processing unit, GPU, okay, because graphic card is just like some smaller computer cluster inside the machine, okay, so the GPU can take we should take advantage of the GPU, okay? Because for graphic, so the basic idea is for graphic processing is that you can kind of cut into smaller sessions and you just deal with it independently, is it each one independent? Because they don't rely on each other, as then you aggregate together, is it? So that's why here for the data training, we can kind of borrow that the concept, okay? And they're over here to also give us some background, okay? Said the challenges to writing code to target GPU, okay? So there are some special package here that's like CUDA and OpenCL that allow us to use GPU, but that's we write code using CUDA or Open is not most convenient, okay, environment, okay. So that what TensorFlow, later on we will say it's TensorFlow. For developer, it's relieve a lot of work, okay. We can, because you can define at the very top abstract layer. You don't need to worry of the processing below, okay. Okay, and so what is TensorFlow? So TensorFlow, it's scalable and it's also multi-platform, okay, for us to run machine learning, okay, especially for deep learning, okay, especially for deep learning. But regarding deep learning, it uses some wrappers, okay, later on we will see, okay. And TensorFlow computation is that it's rely on constructing directed graph. Okay, so the underlying mechanism is directed graph, okay, to represent data flow, okay. Building graph later on, we can also see it's very complicated, but lucky thing is TensorFlow already with high-level API that will make the developer's life easier, okay. Okay, so regarding TensorFlow, so there are low-level API. There is also high-level API. High-level, it's Keras, okay. Wrapper, that's why we mentioned the wrapper. Okay, and with the low-level API, then basically you needed to create a graph. That's why we call it TensorFlow, So basically, you're going to build this graph. That's going to be a lot of work, okay? But for high level one, then we will see it's much more convenient, okay? So that's the concept. Okay, there are some other concepts regarding TensorFlow. We just get to some basic idea, okay, because it's much more complicated. So TensorFlow, because it's built on graph, definitely graph built off nodes, is it? So you have nodes, you have edges, is it? So nodes, edges, that's in computer science we discuss regarding graph, is it? So node can represent in TensorFlow what? It can represent input and output values, okay? And the value is going to flow through the edges, okay? Through the edges, so they are called tensors, okay? So that's the concept. Okay, so later on we will also see, so you can define some operation, is it, on the nodes. So what is tensors, it says? So tensors is just some generalization of scalars, or vectors, or matrices, or something. Okay. And a scalar is considered as a rank 0 tensor. Okay, vector can be considered rank 1 tensor. Matrix then considered as a rank 2 tensor. And the matrix stacked, is it? So you can stack matrix, is it? Then it's a third dimension, then it's rank 3 tensors. Okay, so this is just some idea. Because if you recall, is it, for machine learning, it involves a lot of matrix operation, is it? So that's why we can use this a tensor concept, okay? Okay, that's regarding tensor. So first, let's take a look why we say TensorFlow is going to be very helpful, okay, regarding deep learning. So this is just discussing one single that MNIST image. As we already know, it's 28 by 28 pixels. So that's lead to 784 features. Is it? And then we have, with that classic one, we have 70,000 samples. Okay, just think about the scale of the data, is it? It's huge. But that's compared with a lot of real world one, it's still not too big, is it? Then let's see, if we use the neural network, this is just a single hidden layer. Hidden layer, okay. Single hidden layer. So here we have the imports, is it? The inputs. So this is in regarding each pixel. Is it? So we should have 784 of this. Is it? And assuming the hidden layer, we have 100 neurons. 100 neurons. Is it? 100 neurons. And the output layer, we have 10 digits, is it 0 to 9. So we have 10 outputs. Okay, so that's the neural network diagram, is it, based on what we learned. Okay, then let's take a look how many parameters we needed to optimize. The weights involved, is it? The weights involved, you have 784 inputs and you have 100 hidden layer, is it? And it's fully connected. Neural network, is it? So the total weights here, is it, from input to hidden layer, that's 784 times 100, is it? And plus the bias term. Is it? So we should also have 100. Is it? Okay, and then from hidden layer to output layer, there should be 100 times 10 regarding the weights, and plus the bias term. Is it? So we have 10. So total is 7,900 around weights we need to train. Is it? So it's a lot. There are a lot of weights. Is it? So that's why we said if we use graphic card, then it can help a lot, because graphic card is like a small computer cluster. Is it? Because you have so many weights you need to train. Is it? Okay, so that's the idea, okay, about the level of the computation. Is it? That's why we see that GPU has advantage. Okay. Okay, then next let's take a look the TensorFlow idea, the graph. Okay, so let's take a look. This is a very, very simple arithmetic operation. Is it? So you add two values, you add another two values, then you multiply them. So from this, we say we can break it down into the following components. You can define B plus C to D, is it? And then you can define C plus 2 to E. Okay, and once you have this, then you can define D times E and assign it to A. We can break it down like this. And if we analyze, these two don't depend on each other, because they don't depend on it. So it can be done basically if you just think on one machine, is it? And then simultaneously on another. The idea is that we can definitely do this. You can kind of let two persons simultaneously do this one and do this one, is it? And then that's speed up versus you just use one person, then it can only do this. After it finishes, then do the next. Is it? But then in this case, we can simultaneously do the calculation for D and E. Is it? Okay, after D and E finish, then the one person can do their multiplication. Is it? So that's this concept, okay. And if we represent the concept graphically, then we can clearly see, so this is an input value. This is also input values. Okay, we can draw something like, so this is a node, this is a node, is it? And this is the edge. So here we have node, edge, is it? Okay, then this value and this value both needed to be provided to this node. So this node going to do addition, and this node also going to do addition, is it? So both of this node, they can simultaneously do their work, and then after they finish, they report their work to another node, is it? So then in this case, like over here said, D and E computation can be performed in parallel, is it? If you have multiple CPU, then you can let it do in two CPU, or you can distribute them to GPU to simultaneously conduct the calculation. Is it? Then it's faster. So basically, this is the concept of TensorFlow, okay? TensorFlow. So it's just then with the graph, then graphically we can clearly identify, okay, what job can be done parallel, okay? Then it can be distributed to multi-core or GPUs to do the calculation. Okay, so that's a very basic concept, and we're running out of time. So